Zhang Ling from the East China Normal University. His title is Historical Report Guided Bi-modal Concurrent Learning for Pathology Report Generation. Take your time, thanks.
Thank you. Good morning, everyone. I am very honored to share our work, Historical Report Guided Bi-modal Concurrent Learning for Pathology Report Generation. Pathological diagnosis is the gold standard for tumor diagnosis. However, traditional microscope examination is very time-consuming, and in settings with limited pathology experts, both the efficiency and accuracy of diagnosis are constrained. AI-based automatic pathology report generation holds great potential to address this challenge. The goal of automatic pathology report generation is to input whole slide images and output a complete pathology report containing information such as tumor type, boundary status, and TM stage. Previous work on pathological image captioning mostly focused on small image patches, which is insufficient for large whole slide images. In recent years, research has emerged on whole slide image-based pathology report generation using an encoder-decoder structure to auto-regressively generate reports from the slide. However, generating detailed diagnostic reports from whole slide image faces two major challenges. First, whole slide images contain billions of pixels, including many regions irrelevant to diagnosis. Feeding all patch features into a self-attention-based encoder introduces excessive redundant information, making it difficult to identify relevant regions. Second, there is a large modality gap between pathology images and textual medical reports. Visual features lack semantic guidance, making it hard to generate reports rich in medical terminology. To address these challenges, we drew inspiration from the workflow of pathology experts. Pathologists typically first identify suspicious regions under the microscope and then make diagnostic decisions based on their extensive experience. Accordingly, to tackle the issues of information redundancy and lack of semantic guidance, we propose to mimic this workflow. First, identify key regions and then retrieve similar historical reports to provide semantic knowledge. This knowledge, together with visual information, guides the pathology report generation. Our framework consists of an encoder and a decoder. The encoder has two branches, visual and knowledge. In the visual branch, to extract key image features, we propose a visual token cross-attention module. A learnable visual token is initialized to mimic the pathology viewing perspective and is repeatedly fused with patch features to identify the most relevant image features. In the knowledge branch, to emulate the diagnostic expertise of pathologists, we built a knowledge bank by converting training set pathology reports into feature embeddings. Since the text encoder of existing pathology large models based on CLIP has a maximum input length of 77 tokens, we split long reports into sentences before embedding them into knowledge features, which are stored in the knowledge bank. To mimic the process of diagnosis based on identified key regions, we use key patch features to retrieve knowledge. Specifically, the cross-attention scores from the first layer of the visual branch are used to select high-attention patch feature. These features are aggregated and compared with the knowledge bank to retrieve the most similar knowledge embeddings. The knowledge branch then fills a learnable text token with the retrieved features to extract key semantic information. Finally, the visual and text tokens from the encoder are fed into the decoder to auto-regressively generate the pathology report. We evaluated our method on TCGA breast cancer dataset. Ablation studies show that our visual token cross-attention module and the knowledge branch significantly improve pathology report generation performance. Visualization of the model's attention demonstrates that it focuses on tumor regions and the generated reports accurately describe tumor type, historical grade, boundary status, and TM stage. Comparing the retrieved knowledge with the ground truth reports, we found a high agreement in tumor type, historical grade, and TM stage, validating the effectiveness of using historical reports to assist pathology report generation. Although our proposed dual-branch framework improves the performance of pathology report generation, there remain many directions for future extension. First, the knowledge bank we currently use for retrieval is derived from pathology reports in the training set, which limits the scope of pathological information it contains. This restriction particularly hampers generation when applied to multi-center datasets. In addition, the current framework only incorporates pathological images as input. Other modalities, such as MRI, can provide richer features for diagnosing tumor size and related characteristics. Furthermore, how to design interactive machines that offer diagnostic suggestions in real-world clinical applications is another direction we aim to explore in the future. That concludes my presentation. Thank you.